Hello everyone. So this is our 12th week of the live tutorial session for the NPTEL course Linear Algebra, and today we'll be discussing some problems related to the determinants and volumes. So let me start with the basic requirement which we need for discussing today's problems. So determinants as for matrices is known, and so similarly for a linear map the same determinants is defined. So suppose again the setting is suppose V is a finite dimensional vector space. Vector space over a field K, and say T is a linear map. T is a V from V to V is a linear map. Then we can define the determinant of this function as suppose let V1 through Vn be a basis of V, V over K, and then we can write any image of any Vi under T. We can write that as some linear combination of this basis vector, right? So then if T of Vj equal to sum of Aij Vi, so for I equal to 1 to n, then the determinant of T is defined to be the determinant of this matrix. Determinant of this matrix Aij, Ij both runs from 1 to n, 1 to up to n. Okay, so this is the standard definition of determinant for a linear map in a finite dimensional vector space. And another thing that we need to discuss that the okay, sorry, the screen is not visible, right? Okay, I hope this is visible now. Okay, so I just defined the determinants of a linear map, how to define it, and now I'm saying that how to define the volumes, like how the determinants and volume are related. So suppose we are in Rn case only. Some M is a subset of Rn. Rn as a volume. So this is 1, and this is suppose as a volume, and T is a linear map again from Rn to Rn. linear map. Then the volume of the image of this subset M. Okay, then volume of T of M equal to determinant of T, okay, into volume of M. Okay. So this relation will use in the problem student. So this is also proved in the lecture also. So these two are the main thing that will be used for solving the problems. Okay. So let me go to the first problem. So suppose A is a finite dimensional K algebra. So recall what means a finite dimensional K algebra means. It is a finite dimensional vector space over the field K, and it also has a multiplication structure on it. That means I can multiply two elements in A. Okay, so in other words, it is just a ring with a vector space with a multiplication structure, or ring with a vector space structure. So all the structure are compatible with themselves. Okay, and so that the A, and now on A we can define a map lambda x from A to A just by left multiplication, because the multiplication is defined there. So y goes to xy. So this x is fixed, so I am multiplying each element y and sending it to the xy. Then I need to show that this lambda x is a k-linear operator on A, and as it is a k-linear operator, so in particular if I think A as a k vector space just, so this is a linear operator, and so it has a determinant, and that determinant in this case is called the norm of x. For a particular x belongs to A, if I calculate the determinant of this linear transformation lambda x, then that determinant is called the norm of x. Okay, so first let's see that this lambda x is k-linear, then we'll see this property that this satisfies this property. Okay, so this k-linear is easy. So what we need to show, suppose for let's say CD belongs to K, and A1 A2 belongs to A, lambda x of C1 plus dA2 equal to, this should be multiplying by x on the left and with CA1 plus dA2, and this is again by distributive property in the algebra. So I'll have C into like distributive, and then again if I have multiplied some element of K and then x and then A, this is same as like xa1 this thing plus dx at. So this again I'm using two property. First one is distributive, and then as C and D belongs to K and it is a K algebra, so I can use this also. C I can pull out on the left and do the multiplication first on x and a1 and x and a2. Okay, but what is this? This is C times lambda x of a1, right? And this is d of lambda x. So this is showing that this lambda x is linear, so k linear. So this implies lambda x is k linear. Okay, so now for these properties we need to, so what is it is defined. So nka of x, this is called the norm of x. So this is defined to be the determinant of this linear function lambda x. Okay, so this is the definition of this norm. Now this norm satisfied some condition, we need to check those. So there is a I can define a norm map which takes an element x from A and send it to the norm. So it is a map from A to K. So now for this map, first we need to show that it is multiplicative. That means if I take two element xy in A, first multiply in A and then take norm, that is same as individually I take first norm and then multiply in K. Okay, so let us see that. So by definition, n of xy is by definition it is n a k xy. So this is again by definition determinant of lambda xy. But the thing here, note that lambda xy is also like lambda xy, this is same as lambda x times lambda y. Why? So this is simple. Lambda xy of if I take any z, this is z xy, right? Or no, the other thing. So first xy then z, right? But due to the associativity, this is same as x yz. So and this is lambda x of yz, but yz is again I can write as lambda x of lambda y of z, right? So this implies that lambda xy equal to lambda x into lambda y. So this is happening for all z. So this is I can write just determinant of lambda x lambda y, right? So this is composition, okay, lambda x composition lambda y. But determinant of this composition map is again by property of determinant that it is determinant of lambda x into determinant of lambda y. Determinant of lambda y. But also from this definition, determinant of lambda x is n k a of x, which is just nx. So and the other thing is ny. So that this is true for any xy. So this proves the first property. Now for the second property, what you need to show that if I take any element a from k, then I can take the identity element of a and consider a dot 1. So that is an element of a. So as it is a vector space, so it is just that element. Now if I consider the norm of that particular element, that will be a power n, where n is the dimension of a over k. Okay, so this is also similar. So a is given to be in k, and then n of a, that is not actually defined as my function n is defined from a to k, but I will define that to be simply 1 dot a dot 1 of a. So 1 dot a dot 1 a, this is clearly belongs to a, so it has the meaning. So it is by definition again determinant of lambda a 1a. Okay, but this is again if I use the previous thing, so not exactly the previous thing, but just if I calculate directly of determinant of this function lambda a 1a, so what is it doing? So lambda, suppose we fix some basis, so for a fixed basis, say v1 through vn of a over k. That means I also assuming the dimension of a is k. Okay, so lambda a1 dot a of any vi. This is again by definition a1a with vi, right? But a1a dot vi, that is same as a of 1, so this is 1a vi, this thing, but 1 being the identity element, so this is just a vi. So for all the ui 1 is equal to I is equal to n. So then if I write the matrix of this lambda a, so lambda 1 dot this thing, the matrix of this linear transformation, this is just all the thing is for this one, this is only at the ith position, it is 1. So for the 1 v1, this is at the 1th position, 1th position, it is a, right? So it is clearly a diagonal matrix and all the diagonal entries being a. So this implies that determinant of this lambda 1 dot this thing is a power n, right? So so from this one I get thus n of a is a power n, where n is the, because we assume this dimension of a over k is n, so where n equal to dimension of a over k. Right, so this proves the second one also. For the third one, so suppose x is an element in A, so then we need to prove that it is an unit, that means it has an inverse in A if and only the corresponding norm is non-zero. So k cross consists of all k minus the 0, k minus 0 thing, so this is k minus 0 vector. Okay, so let's put the first forward part. So suppose x is a unit, so what will imply? This will imply that there exists y belongs to A such that xy equal to yx equal to it is enough for me to consider only xy 1. Okay, now just from the multiplicativeness of the this n norm thing, so lambda xy equal to, so lambda 1a, so lambda 1a is nothing but just the identity map, right? So this is identity map of A, and this is equal to lambda 1a, and that is lambda xy, but this is lambda xy is lambda x compose lambda y, right? So yes, so this will imply that determinant of identity of A, which is 1, equals to determinant of lambda x times determinant of lambda y, right? Because determinant is multiplicative for the composition of map, so this is determinant of lambda y, but determinant of lambda x is nx and this is ny. So product, as k is a field, in a field you have two numbers whose product is non-zero 1, right? So neither of them can be so in this case field is also not required. Like this will clearly imply that nx not equal to 0, that is nx belongs to k cross, right? So product of two things is non-zero, so neither of them can be 0, because if any of them is 0, then product is again 0. Okay, so this proves the forward part. Now for the converse part, so again assume that nx belongs to k cross, so that means nx is non-zero, but k is a field. So in this case we are we'll use field that, or do we need to use field thing? Okay, we don't probably yeah, we don't need. So nx belongs to k cross, so this will imply that determinant of this thing lambda x, this is not equal to 0, right? So that's what this means. But if the determinant of a linear map is non-zero, then you know it is proved in class that this lambda x, this map is invertible, right? So this implies this is an invertible map. Invertible map. So in particular, as 1a belongs to a, invertible map from a to a. So this implies as 1a belongs to this here in a, so there exists 1a belongs to a, there exists y belongs to a, such that lambda xy equal to 1a, just by the surjectivity. Okay, and this is also unique y, as this is invertible, so this implies that xy equal to 1, and this implies that x is invertible. Right, so this converse also done, so this completes all the three properties that is claimed here. Now the similar a similar part of this one is in particular thing. So if we consider the algebra A as C, which is an R algebra, and then we need to show that the norm function is actually the usual norm as it is defined in complex number. Okay, so here what we need to see that what is the determinant of the left multiplication by z, right? So in CR of the z, this is determinant of this lambda z. Suppose z so z is a complex number, so let z equal to some x plus iy belongs to C. Okay, so this would write it here. For z equal to this, and now what is so what is the basis of this C over R as a vector space? It has the basis 1 and I, right? So that's the standard basis. So I need to calculate this lambda z on those two bases in terms of again I and 1. So consider the basis 1i of C over R, and then lambda z of 1, this is just z multiplied with 1, so this is z, that means it is x plus iy, and lambda z of I, which is iz, so iz is minus y plus ix, right? So the matrix of this lambda z, the matrix of this lambda z is, so I'll write it is at column, first column, so this is x y and this is minus y x, right? So the determinant, this will imply the determinant of lambda z, this is x square plus y square, right? And x square plus y square is nothing but norm z square. So hence NCRZ is mod z square. Okay. So another instance is another example of such norm thing is, you can consider the all n cross n matrix over a field K to be our algebra A. So there again the matrix multiplication is the multiplication structure, and it is clearly a vector space over K, and it has like dimension n square. So anyway, then here also if we consider the norm function here for any b belongs to m and k, this norm of b is defined to be like, we'll get that to be determinant of b power n. Okay, so again we need to just calculate the determinant of this linear map, like multiplication by b. So, and we'll consider the basis in this case to be the standard basis as Eij, where Eij matrix is the n cross n matrix, so only ijth entry is 1 and remaining all are 0, right? So here also n a k of b is determinant of lambda b or b belongs to m and k. And so consider the basis. Consider the basis Eij or okay, Eij is fine. So 1 is equal to ij is equal to n, or okay, so I need a ordered thing, so this is just a collection, so let me write it is in the ordered way. So I'll first consider it as E11, so write it is above thing, superscript E11 E21 dot E n1, and then like E12 E22 and so on up to En2 and dot up to again 1n through Enn. That means I am considering first as the column thing, like first column all the vectors as E11, this is one entry is only at the 1 position, this is at 2 position, then n1. So I'm going through like column, then first column, second column, third column, and so on. Okay, so this is my order of the basis. So now if I calculate this lambda b of E11, so what is this? This is just b E11, right? But B11, suppose B is let's say, okay, so let's say okay, so let's say B equal to BKL, and KL runs from 1 through n, so this is belongs to k. Now this is by matrix multiplication, so note the only one entry of this E11 is 1, everything else is 0, so it is easy to check that this is actually only survive if I multiply this B matrix with this one, so it will only survive at the it will survive the first column, right? So this is, I'll get actually that a matrix which this is B11, B21, so on up to Bn1, and all the remaining thing are 0, 0, 0, 0, 0, 0, 0, 0. So this I can write simply as sum of I equal to 1 to okay, let me write it P equal to 1 to n, P1 E also P1, right? So because this B11 is B11 times E1 plus B21 into E21 and so on, okay? So this is that. Similarly, if I just do it for, so this is for B11, so lambda E11, so let us similarly do for E, okay, 21 I'll just do 21, 21's mean, so this entry is 1, like, no, sorry, 21 means this entry is 1, so in this case again I will get, so I'll multiply this with this, so this will survive the second column, right? So this is B21, so this will give me again in the okay, so where will I get this? Okay, so just let me write it once. B11, B1n, B1, 2n, Bn1, Bnn, and if I'm multiplying this by 0, 1, all the 0, all 0. So first will I'll get simply B12, right? B12. If I do everything else, so this is 0, 0, all the way up to 0, and then again I will first entry I will get only B22, then 0, 0, 0, and so on up to B2n, 0, 0 up to 0. So just let me do it. Okay, so this is sum of P equal to 1 to n, B P2 E P2, and so this is for the 2 1. Again if I do for 1 2, so this position I'll see that this is again the first column only, right? So if this entry is 1, so everything is 0, then see that this is okay, this is again second column, sorry, so no, so this is again first column, sorry. So for the first, if I have for E11, E12, E1n, if I multiply with B, I always will get always the first column. Okay, and for the second thing, if I do for the second row, if anything, like consider E21, E22, like 2n, always I will get second column in the first row, right? So in general, if I just write lambda b ij, then this will be a matrix. So just a minute. So it will be some equal to 1 to n b p. Okay, so okay, this I probably missed it. Okay, this is not P2, right? This is again, this is 1 1, this is 2, yes. So this is not, this is also P1, right? Because 1 1 entry is 1 2, 2 1 entry is 2 2, and so on, right? So this is missing something. Okay, this one's not EIJ, but this is EIJ. So I'll get at the jth column of this matrix as ith column of B, right? So okay, write that. So okay, just so this is just equal to for the 2 1 entry, so 1, the second j determines the where this will occur, the column will occur. So at the jth column, so this is jth column, the ith column of that will occur is, so this will be B, like this is 2th column. Okay, 1i, B 2i, B ni, and this is jth column. Okay, and remaining all are 0. So this is jth column. So jth column, this. So this I can write as P equal to 1 to n BPI EPJ, right? Yes, BPJ. So this is the in general for IJ. Okay, one decimal. Now if I just write the matrix in the big matrix, so there is n square many, so dimension is n square, so this is n square cross n square matrix, but it has very specific like representation. Note that this is from like P11, P21, Pn1, so this is only appears in the like only this is appearing in B11, B21 in the first n entry, then it is shifted to, for the 2 1 entry, this is shifted to again this is there in the P. Okay, yes, this is again on the P1, but this column is the second column of the B. So then I write the matrix of lambda B. This will be kind of this one. So B1 1 B2 1, so Bn1. Then for the remaining all are 0, right? All the coefficient for E, this thing is 0, it only from 1 to n. And then for 2 1 it is again B1 2 2 2 2n for the first n entry, right? So that means the second column 1 2 B 2 2 Bn2 and so on. So this is actually gives me one copy of B, Bn1 Bn2 Bnn, and all the things here are 0 0. But if I go to the next, like next E12, for E12 I'll get the 1 2, so it is at the second column, it is second column I will get the first row, right? So second column, for the second column the vector start with here, right? So it will start here as again B1 1 B2 1, so on up to Bn1 and so on. So a copy of B n1, so this is again here totally 0 nn, so and so on. So this is actually gives me diagonally all the as entries as like B. So just I will write as B, remaining all entries as like 0. Okay. So this is a block diagonal matrix with the diagonal as B. So this is in shortened notation, this is just B 0 0 0 0 B 0 0 0 0 0 B. So n square cross n square matrix with n cross n block in the diagonal is B, and it can be shown that this, whenever you have a block diagonal matrix with only the diagonal entries are 5, everything else is 0, then the determinant of this such matrix is the individual determinant of the diagonal entries. Okay, so determinant of this thing is equal to the determinant of this matrix, which is determinant of B. Each one of has determinant B, so it is determinant, and there are n such thing, so this is determinant of n. So this implies the norm in AK of B, right? AK of B is determinant of B power n. So there might be something like simpler process to claim that this is B, but for the time being I don't have such anything such simpler case. So if I get something, I'll write in the note and upload in the description box. Okay, so this is all the things about determinant and this thing. Now let's go to some problem related to volumes. Okay, so here we need to calculate the volume of a ellipsoid, which is defined as such that in Rn you define the ellipsoid as the solid ellipsoid as x1 x2 xn belongs to Rn, all the elements, so is that x1 square by a1 square all the way up to xn square plus xn square by n square, this is less equal to 1. So in general in R2 you know this is ellipse. Ellipse is defined as x1 square by a1 square plus x2 square by a2 square equal to 1. So it is when you put this less equal to 1, it has like a solid ellipse. So in this case also in Rn we will call such thing as like solid ellipsoid. So it has a volume. So that volume we need to show that this is some omega n times a1 a2 n, where omega n is the volume of unit sphere, which is again defined to be like x1 square plus x2 square xn square less equal to 1. But initially I just said that how the determinant of a map and volume of a solid is related. So if I just use that, so these two like solid thing ellipsoid and this unit sphere, they are related through a linear map, right? I can just shear every coordinate by 1 by a, as ai these all are non-zero, so I can shear this each of this x1 x2 xn coordinate by 1 by a1 1 by a2 1 by an. Okay, so consider T from Rn to Rn by, so what it does, takes x1 through xn and send it to x1 by a1 x2 by a2 xn by an. Okay, so this is clearly a linear map, and if I calculate the determinant of this t, so t sends e1 to 1 by a1 into e1, so t of ei is the standard basis of Rn, so t of ei is sends 1 by ai times ei, right? So this is again, so for all I equal to 1 to n, so this will imply that the matrix of this T is a diagonal matrix with the diagonal entries as 1 by a1 1 by a2 1 by an. So that means the determinant of this T is 1 by a1 up to 1 by an, right? So this is just 1 by a1 into an. As all the AIs are non-zero, like so this is well defined. So in particular this T is also invertible. Inverse is clearly given by x1 goes to ax1, right? So anyway, so suppose this ellipsoid is let's say E, and this sphere is M. Okay, so by this transformation is clearly see that if I take the E is just T of M, right? Because T of M will be T of x1 x2 xn such that x1 square plus x2 square xn square less equal to 1, but T of x1 x2 xn square, that will be okay, there is something. Okay, yes, that's trying to think. Okay, this is not the case, the opposite thing is the case. So okay, E is actually T inverse, so this is anyway invertible, so T inverse of M, and the determinant of T inverse is determinant T whole inverse, right? So the determinant of T inverse is a1 a2 an. So I can directly could have defined this T as x1 x2 xn. Then clearly we see that E as T inverse of M. Now the volume lambda n, so then using the previous thing that like initially what we have the relation between volumes and determinant, so this is volume of E equal to determinant of T inverse into volume of M. Now volume of M is given as this omega n, so this is, and determinant of T inverse is determinant T whole inverse, so determinant T whole inverse into omega n, which is just omega n a1 a2 dot dot an. Okay, so this proves this thing. Similarly for this one, so this one again is given as f1 f2 fn as a basis of the linear forms on Rn. That means Fir belongs to Rn, the dual of Rn, so Rn star, and E1 star, E2 star, En star are the standard dual basis of the standard basis, with respect to the standard basis E1, E2, En of the Rn star. And this A, this script A is the change of basis, like transition matrix for these two bases. And then the determinant of this D is the determinant of this transition matrix. Now if we define a this volume, so again say this as M, x belongs to Rn, such that mod of Fix, so Fix is a real number, so this is bounded by some Ci are non-negative real numbers. So this has the volume, so 1 I is equal to n, so this has the volume as 2 power n C1 C2 Cn into D. So this is easy actually. This is again the using, so if I define a f from Rn to Rn by just, let's say x1, so just x goes to f1x all the way up to fnx. So this is a clearly, as f1 f2 fn all are linear, so this is a clearly linear map. And the determinant of this thing, so, and determinant of f, actually one can check that this determinant of f is actually the determinant of, so determinant of this matrix. Okay, this matrix, and this is to be D, and this is invertible actually, as D is given to be non-zero. Okay, so this is not okay, anyway, this is belongs, if this is invertible, so this D is non-zero, and this will actually inverse the determinant of F inverse is 1 by D, right? And then this M is nothing but F inverse of the usual, like if I say Q is,
Yes.
so this is x belongs to Rn, or let's say just x1 through xn, this belongs to Rn, such that mod xi is less equal to Ci. That means it is the cube, so cube with the ith is so usual cube has like 1 minus 1, 1 minus 1, all length are 2. So in this case actually at the ith direction you have length 2 Ci. Okay, so, and so this is a cube, and its volume is actually 2 Ci is in 2 Ci in ith direction, so 2 C1, 2 C2, 2 Cn, so it has 2 power n into C1, C2, Cn, this has volume, and it is easy to say that this is F inverse of Q only, the defining M. Okay, then this again implies the volume of M as 1 by D, which is the determinant of this F inverse, into the volume of Q. Volume of Q is 2C1 to C2, so 2C1 to C2 all the way up to 2Cn product by D. So this is 2 power n C1 C2 Cn by D. Okay, so this is the required thing. So there are little bit of thing there to check or this thing. So first of all, this why this determinant of this F is determinant of this transition map, but if we write it, it will be clear. So if we use this thing in the next problem, so in this thing actually you need to use this problem to calculate the volume of these two parallelograms. Okay, so in R2 you can, if you have linear function, so here just take for the A, I'll just say what. So in the previous thing we just have seen that if we have some solid thing which is given through some linear function fi from Rn to R, so then this thing is equal to this one. So in this case also note that this, if I define f1 of x1 x2 as x1 minus half x2, that is a linear functional on R2. Similarly, if I define f2 x1 x2 as the other thing minus x1 plus x2, then the first q is nothing but all x belongs to R2, such that mod of fix, okay, so I can't say, so because they are different C1 C2, so mod f1x is less equal to 3 by 2 and mod f2x is less equal to 2. So here C1 is 3 by 2, C2 is 2. Then just from the previous thing, volume, volume of this Q is determined, you need to calculate the determinant of the transition matrix. So the transition matrix in this case, this, so this thing is actually 1 half minus 1 1. Okay, so determinant is in this case, give me something, is 1. Okay, so okay, fine. So this is the transition matrix. Then so let me see, so I should have fi equal to h into, yes, so this is the transition matrix. So 1 minus half, so this is half, determinant of this thing is half, and C1 C2 is, so determinant of this thing D equal to half, and then volume of this Q equal to just, in this case n equal to 2, so 2 power n into C1 is 3 by 2, C2 is 2 by D is half. So this 2 to cancel out, so we have 8 into 3 into 2, so 40. Maybe did I miss something? Yes, it is 3 by 2 2 square, 3 by 2 2, yes. So similarly we can calculate the determinant of volume of this second thing also. Okay, so it's already time. So is there any other question? I'll stop here. Okay, so then let me stop here, and this is the last meet. So Thank you everyone. Yes, thank you. Okay, so bye then.